Welcome. This video is all about manipulating formulas. These are the kinematics equations or formulas from the datasheet, the ones that we'll be using in this unit. And one of the skills that you need to develop is you need to be able to rearrange these equations to solve for different variables. So I'll be showing you how to do rearrange or manipulate these formulas in a few different examples in this video. Here's one of the first formulas that we learned in Physics 20. This one is for speed or velocity equals distance over time. If you're finding velocity, then you just need the distance and time. But what if you need to solve for the distance or displacement? Then you need to rearrange this formula. So instead of v equals, we want something that says d equals. So the way that we can do that is what we're going to be doing a lot of times, or all the time here, is do the opposite operation. So what I mean by that is instead of we want to isolate t, we want d by itself, so we can multiply both sides by t. Instead of dividing by t on the right, we multiply both sides by t, and these t's cancel. And then we get t times v equals d, or d equals v times t. So distance or displacement equals velocity times time. Same equation again for velocity, distance over time. This time we want to solve for time. So in a problem you're doing, maybe you know the distance and speed or velocity, and you want to find the time. So we want to rearrange this so it says t equals. So t is on the bottom of this fraction, d is divided by t. So the way that we can move it up is if we multiply again both sides by t. On the right side, t's cancel, and we get t times v equals d. And then we want t, so we do the opposite. Instead of multiplying by v, we can divide by v on both sides. Always do the same to both sides in equation. And then v's cancel here, and we have t equals d over v. So time is distance over speed, or time is displacement over velocity. Here's an equation for acceleration. Acceleration equals the difference between final and initial velocity divided by the time. But if we want to solve for the time, t, we need to get this formula rearranged so that it says t equals. And we have t on the bottom of this. This is just really a fraction here, or this is vf minus vi divided by t. So again, we're going to do the opposite. And the opposite of divide by t is multiply by t. So multiply both sides by t, and we get t times a. On the right side, the t's cancel, and we get t times a equals vf minus vi, and we want to solve for t, so the last thing we do here is divide both sides by a, just like we did before. We do the opposite here, so we divide by a on both sides, and we get t time equals final velocity minus initial velocity divided by acceleration. Same equation again for acceleration. This time we're solving it for final velocity. So VF is right here. It's part of this fraction, and on the right side here. So the first thing we can do is, again, multiply by t. We want to get rid of this, basically this fraction here. So then we have t times a equals vf minus vi, and we're solving this for vf. So we need to get rid of the VI here. It's really minus VI, so again, we're going to do the opposite. So the opposite of subtracting VI is to add VI to both sides. And so we get 0 on this side, and then we have VF by itself. On the left side here we have T times A, or A times T plus VI. So remember also, if there's no symbol in between the variables are touching, this means multiply. So we can write this the other way. Some people prefer, we usually write it this way, right? Just flip it. So the final velocity would be, and we can change the order here too because we're just adding. And this is a good way to look at it. If you really think about what this formula says, it tells you that the final velocity of an object is due to its initial velocity plus any acceleration and the time that it's been traveling for. So if there was no acceleration in this case, for example, if A was 0, then we would have just VF equals VI. So the final velocity would be the same as the initial velocity, which would be constant velocity, no acceleration. But if there is acceleration, we always have to include it. Same equation again. This time we're solving for VI, so it's going to be similar to the last one. VI is on top, but it's kind of like a negative VI here. So just like the last time, we're going to multiply both sides by t. First step to get rid of this fraction. So then we have t times a, or TA equals VF minus VI. And we want VI by itself, so there's kind of two ways to go. We can move the minus VI to the other side, or we can move the VF to the other side. I'm going to, well, I'm just going to leave the VI here. I'm going to subtract VF from both sides. So we get, on the left side, A times T minus VF equals minus VI. So this is almost what we're looking for. We don't want VI to be negative here. So the way that we can do that is multiply both sides by -1. Or we could have moved over the minus VI to the other side instead at the start there. If we multiply both sides by -1, what happens is these signs are going to change. So we have -1 times AT minus VF equals -1 times negative VI. And so the signs are just going to change inside the brackets here. So VF will be positive and AT will be negative, and this will give us VI. So you can flip it again. If you like, VI equals VF minus AT. So the initial velocity is equal to the final velocity minus any acceleration that the object experienced. So similar to the last one. Solving this distance formula for t, rearranging it to solve for time. Time is over here. It's multiplied by this fraction here. So we basically need to get rid of this whole fraction on the right side. So we can do it in steps. The first thing I would do is that we can multiply both sides by 2 to get rid of the 2 on the bottom, but make sure we do it to both sides. So we get 2 times d equals VF plus VI times t. And then we want t by itself, so we need to get rid of the brackets here. Remember, right here, the brackets are multiplied by t. So we're going to do the opposite to get rid of it on this side. Do the opposite. Opposite of multiply is divide. So we're going to divide both sides by VF plus VI. So you can divide by the whole, everything that's in brackets there. But we do it to both sides. And on the right side, the brackets cancel. and we get t by itself equals 2d over the final and initial velocity as a sum. So let's take a look at solving this equation for VF, for final velocity. So again, VF is in this fraction on the top here. So we want to basically break down the fraction. It's also multiplied by t here. So maybe the best step to do first is to divide both sides by t. So we can do that here. I'll just write it like this. This is like a compound fraction, but it still works the same way. We can cancel the t's and we get d over t equals VF plus VI over 2. This is interesting because this is d over t is like our average velocity formula, which is the left side of this equation, and the right side is average velocity as well if we take the sum and divide by 2. But we want to solve this for VF, so we have to keep going, and again we have a fraction divided by 2, so we can do the opposite and multiply both sides by 2. So we can technically maybe put brackets around this, both sides multiplied by 2, and then on the right side the 2's cancel, and we have 2d over t equals VF plus VI, and then we want VF by itself on this side, so we can take away VI on both sides. So VI is gone on this side, and we have VF by itself. VF equals 2d over t minus VI. Another thing it's important that you can do is look at the formulas. They need to make sense as far as the units go. So if you have a formula for distance, the units have to work out to units of distance. If you remember, the standard units are meters for distance, seconds for time, and kilograms for mass. I won't be using any kilograms till a little bit later. But make sure your distances are in meters and seconds, and then if you look at the formula you have, if you look at just the units, the final velocity would be meters per second, and then 2 times the distance would just be meters. Over time in seconds would also be meters per second. So basically what I'm saying is you have to have like terms here. So meters per second, so the last term also has to be meters per second, which it is because it's a velocity. So you can see by looking at the units that you're going to get an answer in meters per second, which is what you want for velocity. Solving this equation for A. So this is, you could say it's a distance or a displacement equation from our first unit from the data sheets. In this case, we have an example where VI is 0, which is many times the case. The initial velocity is 0 if the object starts from rest. So sometimes they'll say in a problem an object starting from rest, so the initial velocity is 0. This is also the case when an object is dropped. So if you drop a ball, the initial velocity is 0, and then it speeds up as it moves towards the ground. So in this case, if VI is 0, this equation becomes a lot simpler. VI is 0, so we have 0 times t for that first term, so that just gives us 0. So this first term is gone when VI is 0. So we're left with just d equals 1/2 at squared, and we want to solve it for a. So if we can divide by t squared first, or we could multiply by 2 first to get rid of this fraction. I'm going to divide by t squared on both sides. So the left side is d over t squared, and the right side is that 1/2 is still there, 1/2 a. And then we just need a by itself, so we want to get rid of the 1/2. So instead of dividing by 2, we do the opposite and multiply by 2. That will get rid of that fraction. So multiply both sides by 2. The 2's cancel here. And then we have a by itself on the right side. I'm just going to flip it so it's on the left. So a acceleration is 2 times d over t squared. And again, you could look at the units. The units, if you remember, for acceleration are meters per second squared, the standard units for acceleration. So we have meters per second squared on the left side. We have to have meters per second squared on the right side. If you look at the top, it's 2 times distance, which would just be meters, divided by time in seconds, but it's squared. So seconds squared. So we have the units all work out. Meters per second squared on both sides of the equation. Same equation again, same situation. Assume the initial velocity is 0, or maybe you're doing a problem where the initial velocity is 0. This time we want to solve for t instead, so solving for time. If vi is 0, this equation again, the first term is going to go to 0. If you remember from the last example, we have 0 times t is 0, so we're left with just d equals 1/2 at squared. And we want to solve for t, so we want to get t squared by itself. So I'm going to multiply by 2 to get rid of the fraction. Multiply by 2 on both sides. And the 2's will cancel here. And 1 times at squared is just at squared. And we're solving for t, so we can divide both sides by a. Now we have t squared equals 2d over a. And we want t, not t squared. So again, we're going to do the opposite of squaring, is square root. So if we take the square root of both sides, square root of t squared is t, and then the right side, we have to do the square root of 2d over a. So this would be something you would end up doing if you were maybe a problem where you drop an object. Maybe you drop a ball. So the initial velocity would be 0. The acceleration would be 9.81 meters per second squared. The acceleration due to gravity. So you could, if you knew the distance here, maybe you would be finding the time, how long it takes an object to fall from a certain height, where d would be the height. Final equation, solving for a acceleration in this formula again. So acceleration is over here. It's multiplied by d and by 2. So our first goal is to get this term by itself. So we can take away vi squared on both sides. So the left side is vf squared minus vi squared. We got rid of vi squared here. That's equal to 2ad. We're solving for a. We can do now this in 2 steps or in 1 step. We can divide by 2 on both sides, then divide by d, or we can do it all at once. I'm going to do all at once, so divide both sides by 2d. 2 cancels 2, d cancels d, and we have a by itself. So the acceleration is the difference between the final and initial velocity squared over 2 times distance. And again, units of acceleration, just to make sure you rearranged it right, the units need to work out. So the units for acceleration are meters per second squared. So for a, we have meters per second squared. Vf squared or vi squared, if you remember, the units for velocity are meters per second, so velocity squared both get squared. So we have meters squared per second squared. Meters squared per second squared on the top minus, again, meters squared per second squared. And I'll just put it in brackets. The whole thing is divided by 2 times the distance, which would be meters. So we end up with meters squared minus meters squared over meters. We can cancel the meters here. And we see that meters squared is the difference between meters squared minus meters squared. So the units all work out. So this is kind of a unit analysis that you can do. Check the units if you're not sure. Your units need to be the same on the left and right side of the equation.